What is up, Precalculus? This is lesson 12.4. We're going to be talking about instantaneous rate of change and also derivatives. Technically, instantaneous rate of change is 12.3. We're going to put it in with this lesson because it kind of makes more sense to go there. So before we actually jump into what that means, let's do just a little bit of recall here on what the rate of change kind of is. So if you were to go on a hike, and you start off, you haven't gone, you start off, you don't have any time spent yet, and you haven't gone anywhere. And then after 1 hour, say you've gone 3 miles, and after 2 hours, you've gone 6 miles. So if we want to talk about this rate of change, we'd see, well, how much distance have I changed divided by how much time have I spent? So we have this point up here that is 2, 6, and we have a point here, let's say, that is the point 1, 3. So if I wanted to find that rate of change, I'd just say 6 minus 3 over 2 minus 1, right? The change in the y, 6 minus 3 over the change in the x, 2 minus 1. And that's going to give you 3 over 1, or 3. And since this is miles an hour, we'd say 3 miles per hour. So as we went on this hike, our rate of change was 3 miles per hour. Which you would notice if you were to look at the equation of this line, which is y is equal to 3x, you'd notice that 3 miles per hour is just the slope of this line. So if we're talking about a linear equation, the rate of change is very easily, it's just the slope. But let's just think about realistically, if I was going on a hike, I would not have instantaneously gone from a stop to going 3 miles per hour, and there's not really any way that I held that speed the entire time. As I walked for 2 hours, I went exactly 3 miles an hour the whole time. Same thing maybe if you were with a car. There's stop signs, you have to speed up, you have to slow down, different speeds on the highway versus on the side roads, etc. So really, my speed wouldn't be linear. It'd probably look something more like this. All right, I'm speeding up, and then I'm slowing down, I'm speeding up, I'm slowing down, etc. I don't know exactly, but the idea would be is that the slope, or my rate of change, would kind of start off slow, and then it would increase and then go slower. It wouldn't be a straight line. So if I wanted to talk about my speed or my rate of change on a line like this, I couldn't talk about the rate of change. Over here there is a single rate of change because it's constant the whole way through. But over here I wouldn't be able to say the rate of change is at a particular point. I couldn't say the rate of change because over here I'm not going as fast, but right here I'm actually going pretty fast. I'm running downhill or something. So the rate of change at different places is going to be different. And that's actually what we're going to talk about here on the next slide. So just for simplicity's sake, I have thrown up a quadratic equation here, and I've graphed it for us already, so that we save a little bit of time. So we're going to be talking about what is the rate of change, and our expression is what is the rate of change of this function f of x at or whenever x is equal to 3. So right here at this point, how fast am I changing? And really what it's asking me is the slope of a tangent line. Remember, a tangent line just kind of sets on the edge of this and just touches at one particular point. So you notice if this was talking about, I guess, me walking, here I'm moving at a negative rate of change, right? I'm moving backwards, I guess. And then here I've stopped, and then here I'm going back up in a positive direction. So we're actually talking about the tangent line right here at this point that just has this one point in common, nothing else touches. So what we need to do is we need to try to find the slope of that tangent line. That slope of that tangent line would tell me how fast I'm changing as I'm on this point, as I'm on this graph right at this point. But the problem is if I want to find the slope of this line, I actually need to know more than one point. I have one point on here, and if I had any other point on this red line, then I could find its rate of change. Say if I had this point over here, then yeah, no problem. Change in y over change in x, there's the rate of change. But the problem is I don't know another one. I just have this one point right here that's at 3, -4. That's the only point I have. So what I'm going to do is, instead of finding the actual slope of this red line, I'm going to just estimate the slope of this red line. And I'm going to pick, with this yellow line, I'm going to pick 2 points that I can find, here and here. And I'm going to find the slope of this line, this yellow line. Okay, well, the slope of that yellow line is not too bad, right? It is at the point, I have to use the point 4, -1, and the actual point that we have there, which is 3, -4. So change in y over change in x would look like this: y2 minus y1, x2 minus x1, which is going to come out to be -1 plus 4, so it's going to be 3 over 1. So the slope of this yellow line is 3, and that's a pretty close estimate. Okay, so I would say, hey, at this point, my rate of change is about 3. It's actually maybe a little bit less than that, but I'm just saying, hey, about 3. But someone says, I don't want about, I want to know the actual one. I'm like, okay, well, let me see what I can do. What I'm going to do is I'm going to pick a more accurate point. Let's pick a point closer. Let's go maybe right in here. Okay, and so I'm going to use this point and this point. So notice, originally, whenever I was with yellow, I went over 1 unit. And now that I'm in purple, I'm just going over a half unit, right? 1/2 of a unit. I'm going to use the slope of this line. Now, look, if we're looking at this purple line, notice it's not the same as my red one, which is my goal. However, it's going to be more accurate than my yellow one that I just created. So I'm just going to make up whatever point this is. We could actually calculate it. Actually, let me go ahead and do that. Okay, so we plugged in 3.5 into this equation, and we got -2.75. So the point 3.5, -2.75. And the actual point that we're wanting at, 3, -4. So y2 minus y1 over x2 minus x1 is going to give us 1.25 over 0.5, which is going to give me 2.5. Okay, so I'd say, okay, 3 wasn't close enough, so it's actually about 2.5. Well, again, they say, hey, I didn't want about 2.5. I want to know exactly what that rate of change is. Well, how would I become more accurate? Well, versus going over 1, versus going over half, let's go over a quarter. Let's go over an eighth, or 1/16, or something like that. The idea is that this point would start moving closer and closer and closer to the one I'm actually looking for. The slope of this line would approach the slope of this line that I'm looking for. But really what we're talking about is this distance over here is shrinking. The distance between my first x and my second x is shrinking. So generically speaking, I'm going to use green here. So this is my actual point that I want, and here's some other point that's on my graph. So this point is at x, comma, f of x. And this one over here, right, this is the x value and this is the y value evaluated at that particular x. Up here, this one over here, I've moved over some distance and that distance we're going to call h. And it's going to be a small distance. We don't want to go a lot, just some distance. So this point over here is going to be x plus h, right? Because if this is x and then this distance is h, it's going to be x plus h. And then that's going to be the function evaluated at x plus h. So its rate of change would be, forget that, f of x plus h minus f of x. I'm going to divide that, right, this value minus this value, divide it by this minus this. X plus h minus x. So if we simplify this down, the top would look exactly the same. F of x plus h minus f of x. But the bottom, notice I have an x minus an x. So it's going to be just over h. But we don't want to just look at this, because that would just give me some estimate. What I want to look at is, what does this value approach as that h goes to 0? So what is the limit of this function as this h value, as the distance between these two gets narrower and narrower and narrower? These values should hopefully approach something, the 3, 2.5. What does this get closer and closer to? So let's see if we can actually do it for this one here, for whenever x is equal to 3. So let's actually use the function we have. So f of x plus h, so we're looking for the limit as h approaches 0 of my function of x plus h. So this is going to be 3 plus h squared minus 4 times 3 plus h minus 1. So what we just did is I plugged x that we want plus h into this function. And then I'm going to subtract the function evaluated at 3. So it's going to be 3 squared minus 4 times 3 minus 1. Divided by, we could plug in 3 plus h minus 3. We realize it just simplifies down to h. So let's go ahead and expand this up here on the top. It's going to be 9 plus 6h plus an h squared minus 12 minus 4h minus 1 minus 9 minus 12 minus 1. All divided by h, and I'm sorry, this is the limit as h approaches 0. So let's see if we can simplify down some of these. I'm going to go ahead and get rid of parentheses, because I'm minusing all of these. It's going to change the sign of each of these. So I'm going to have the limit as h approaches 0 of 9 plus 6h plus h squared minus 12 minus, this is supposed to be an h, sorry, minus 4h minus 1 minus 9 plus 12 plus 1 all over h. Now let's find some things that reduce. I have a 9 and a negative 9. Those go to 0. I have a negative 12 and a plus 12. I have a negative 1 and a plus 1. Now let's find some things that combine together. I have that 6h and the negative 4h. So my next line would look like this. The limit as h approaches 0 of 2h, because 6 minus 4 is 2, plus an h squared all over h. Notice I could factor out the top of that there to have an h. This is going to be a 2 plus an h over h. And then those h's reduce, which would just give me that 2 plus h. So let's look at now, we have the limit as h approaches 0 of 2 plus h. Well, now we can evaluate this. What does 2 plus h come out to be as this h gets so close to 0 that it really pretty much becomes 0. So pretty much what we're doing is we're just going to plug in that 0 in here for h. What does this come out to be? Well, it would just come out to be 2. The limit of that would just be 2. So the slope of this red line that we're looking for over here is 2. So here's one of your homework problems. It says for each problem find the instantaneous rate of change of the function at the given value. So we can kind of skip all that picture and stuff if we want. The picture is what we're doing, but we can kind of just jump right into that with the limit as h approaches 0 of the function evaluated at -2 plus an h. And then I'm going to subtract the function and divide that by h. So this is going to be the limit as h approaches 0 of -2 times -2 plus h squared minus -2 plus h minus 1 minus -2 times -2 squared minus a -2 minus 1. All of that over h. I'm going to pause the video and simplify this out a little bit just to save a little bit of time. Pow. Okay, so I just FOILed this to get this. It's distributed in that negative to get these. That squared is this. This is going to give me -8. And then I distribute in this negative into each of these. Distribute in the -2 into each of these to get these. Feel free to pause it and check my work if you want. But now we can do the job of reducing. Notice I have a -8 and a +8. I have a +2 and a -2. I have a -1 and a +1. I can combine that 8h and a -h, so this is going to give me the limit as h approaches 0 of 7h minus 2h squared all over h. If I factor out the h on the top, I would have h times 7 minus 2h over h. Those h's would reduce, and I'd be looking for the limit as h approaches 0 of 7 minus 2h. And as h goes to 0, this term right here would go to 0, so just be 7 minus 0. So that means this is just equal to 7. Now, as much fun as that is, if I wanted to find the rate of change for the same function at a different point, say 5, I have to go through this whole long process again. And then if I wanted to find it for a different point, say 3, I have to go through that whole long process again. So wouldn't it be nice if I could just do this, but versus plugging it in at a particular point, just leave it in terms of x. So I could find the instantaneous rate of change for this particular function. I could just plug in the value of x. And that is the definition of derivative. Okay, so if we have some function f of x, f of x. If we wanted to find the rate of change of this function at any particular point, we call that the derivative of f of x, or f prime. And to do that, we just take the limit as h approaches 0 of the function evaluated at x plus h, and then subtract the function, and then divide that by h. And the idea would be is that we're going to have something, we're going to find the derivative of this. So my answer is still going to have an x in it, but that derivative is going to tell me the rate of change of this function at whatever point I want to plug in. So if I want to know -2, I can plug in -2. If I want to plug it in at 5, I can plug in 5. So it'll be a function that describes the rate of change of this function, and we call it f prime of x, or the derivative of f. And so this is same formula here. This is what we call the definition of derivatives. So it says use the definition of derivatives to find the derivative of each function with respect to x. So we're going to do the exact same thing we have been doing, except we're going to leave the x's in it. So we're going to do is we're going to find the limit as h approaches 0 of this function right here, evaluated at x plus h. So it's going to be 5 times x plus h squared plus 5 times x plus h plus 5. So again, this is just this function right here, evaluated at x plus h. That's what we're trying to do. And then subtract the function just evaluated at x. Well, this is the function evaluated at x. So it's going to be 5x squared plus 5x plus 5, and then divide that by h. So let's do a little bit of the legwork over here on the right. So x plus h squared is the same thing as x plus h times x plus h. And if I were to FOIL that out, first would be x squared, outside would be x plus 8, not x plus h, but xh. Inside would be xh, and last would be h squared. Combining those like terms would give me x squared plus 2xh plus an h squared. So then this is going to give me 5 times that. I'm sorry, because I have 5 times this, so 5 times this. So I'm just going to try to write it out here. 5x squared plus 10xh plus 5h. Then I'm going to have plus 5x plus 5h plus 5. I just got that from here and here. So this is this. Then I'm going to subtract this thing, and I'm going to have a hard time fitting it, so I'm going to write it underneath. So minus 5x squared, I'm going to write it underneath that one, 5x squared, minus 5x, minus 5x, minus 5. Again, the minus is because minus this, minus this, minus this. So I just wrote it underneath. So notice those would just those would go to 0, those ones go to 0, and those ones would go to 0. So my numerator would simplify down to 10xh plus 5h squared plus 5h. So then we'll have the limit as h approaches 0 of 10xh plus 5h squared plus 5h all over h. If I factor that h out of all of that, I'll have the limit as h approaches 0. So notice I'm going to factor the h out of all of these and then reduce the h with the denominator. So I'll end up with 10x plus 5h plus 5, right? Because that h reduced, one of those h's reduced, and that h reduced. So now the limit of this, as h approaches 0, well, this term would not change as h approaches 0. This term would not change as h approaches 0, but this one would approach 0. So the limit of this is going to be 10x plus 5. And this is a derivative, so I could say f prime of x is equal to that 10x plus 5. So I'm able to, if I wanted to find the rate of change of this function when x is equal to 2, I just plug it in there. It'd be 10 times 2 plus 5 more. If I wanted to find the rate of change of this function at negative 14, just plug in negative 14 into there, and I would be able to find the rate of change of that function. Your homework is a worksheet. Again, I have done 2 of them off of there, and there is only 10 problems, so hopefully it'll save you a little bit of time. If you guys have questions, feel free to let me know, and I'll be happy to help you. Good luck, guys.